Hello, welcome to the new work, a Bayesian permutation training deep representation learning method for speech enhancement with variational autoencoder. And I'm Yang, and I'm from the Honorable University and the CAP 2E. In this presentation, I will first give a research background and after that, I will indicate the highlight of a research. Then I will explain the more details about our proposed method. Finally, I will give the experimental results and draw some conclusions in our research. First, let's learn about the background. As we know, the purpose of speech enhancement is to remove the background noise from the noisy environment and improve the quality and the intelligibility of the noisy speech. The main purpose of the speech enhancement is helping machine understand and helping human understand. The difference is that for the machine understand, when we more concern the word error rate, and this means that we need to obtain the useful features from the observed signal. However, for the human understanding, and we need to play back the original signals, and because we want to listen to some more details, and this is different between the human understanding and the machine understanding. And the potential application of speech enhancement includes some ASR hearing aid system and the teleconferencing, like some Teams or Zooms. At present, the DM-based speech enhancement has been widely developed. However, the main drawback is that the generalization ability of this method is not always satisfactory, especially in some complex noisy environment. To mitigate this problem, some semi-supervised DM-based speech enhancement is developed. The general strategy is that this method uses a DNN like some way to model the speech signal, and the noise is modeled by some NMF model. And they use the EM algorithm to optimize the model and for the speech enhancement application. And to some extent, this method can mitigate the generalization problems in the previous way-based method. And that after that, and I will indicate the highlight of our research. The drawback of current way-based speech enhancement method is that first they need to use a noise to model. They need to use the NMF to model the noise, and this means that they cannot use a linear model for the signal estimation, and this may degrade the speech enhancement performance. And another important issue is that this method cannot disentangle the speech and the noise latent variables from the observed signal. So in this work, and we propose several strategies to address above problems. Firstly, we propose we can disentangle different latent variables for the speech enhancement. This means that we can use the representation learning to analyze the speech and the noise signals in the observed signal. Additionally, in our proposed methods, the noise is modeled by the VE rather than the traditional NMF. And this means that we can use some nonlinear model to map the signal. Our work also derives a novel VE lower band, and this means that we can use a supervision method for VE for speech enhancement. Finally, our conclusion is that our learned latent variables are attributed to the different types of the signal. This means that for each different latent variables, we can generate the desired signal, and their combination can be also used to generate the new signals. Next, let's see the more details about our work. And this is the signal model, and we still consider to achieve the speech enhancement in an active noisy environment. For simplicity, and we use YSD to represent the log power spectrum of the observed signal, speech, and noise, respectively. And this is our model assumption for the proposed method. For the generative model, and we assume that Y is generated from a random process involving the speech and the noise latent variables. Here, we assume that the speech and the noise latent variable are independent, and the observed signal X and D can be also drawn from the latent variables. And for the recognition model, and we assume that the latent variables can be estimated from the posterior distribution, or they can also estimate from the observed signal posterior distribution. To obtain a good signal model, we have this conditional assumption. Also, we cannot 100% to ensure this assumption is correct, but we can ensure that our model can disentangle different latent variables from the observed signal. And this is very different from the previous VAE-based method. And this is the framework of our proposed method. We can find that there are 3 ways in our proposed method. We firstly to use a noisy way to estimate the different latent variables from the observed signal. And after that, we use the estimated latent variables as the input of the decoder of the clean speech and the noise way to obtain the real probability distribution for the speech enhancement application. To achieve the purpose, and we need to based on the lower band. If there are multiple latent variables, the VAE lower band can be written as the equation 2. The L can be read as 3, and there is a related parameters for the estimation. Our purpose is to maximize the equation 2, and this is equal to minimize the equation 3. Based on our previous assumption, the equation 3 can be further written as the equation 4, like this. And this is here is we want to obtain the speech and the noise latent variables from the observed signal. So we propose a Bayesian permutation training process between the 3 ways. To achieve the supervision learning purpose, we add an attention mechanism in the calculation of the equation 4. In the first term, and we add this attention mechanism, we introduce the calculation of the clean signal. And this means that we can use the speech information to train the noisy VAE. So the first term in equation 4 can be written as the equation 5. Similarly, the second term can be written as a similar form. So the final loss function can be written as equation 6. In equation 6, we can find that there is a KL divergence constraints for the speech and the noise latent variables, which ensures that the posterior distribution can be closed under the supervised learning. Moreover, minus L can be used as a new variational low band to perform the supervised VAE training in other VAE-related applications. Here, there is a training tricks. Based on the equation 6, we use the clean speech and the noise VAE loss function to perform the joint training, and this can optimize the noisy VAE speech enhancement performance. And let's have some algorithm to the proposed algorithm. For the proposed algorithm includes a training and an enhancement stage. The whole training process can be described as this figure. First, the CVAE and the NVAE are separately pre-trained without any supervision. Then the LPS feature of the speech noise and of the signal are separately used as the encoder input of the CVAE, NVAE, and NFAE to estimate the posterior distribution and the rear distribution based on this equation 6. Finally, we use equation 7 as a loss function to perform related parameter update with some SGD algorithm. The training is completed when the neural networks convergent. In the online speech enhancement stage, and we only need to use the structure in the blue frame rectangle. And in the online speech enhancement stage, we assume that the ZX sampled from the PZX is approximately equal to the sample ZX from the PZXY, and we can use it as the input of the decoder for the speech enhancement. Next, let's see the experimental result. Now we will apply the two experimental to evaluate the performance of the proposed method. At first, we will use an example to verify that our method can distinguish different latent variables from the observed signal. After that, an experimental will show the performance of the proposed method. And this is dataset, and we use the timid dataset and the noisy X92 and 100 environment noise dataset. And this is signal settings. And next, let's see the baseline, and we use the Bayesian as the baseline. And this is similar to our proposed method. The only difference is the training loss functions. Our training loss functions can perform some latent variable learning, but the reference cannot. And this can more directly to show the benefit of our proposed method. And this is some neural network settings, and we use 1D CNN to perform the experiment. Firstly, we vary the performance of the disentangle, speech, and the noise latent variables. Based on our assumption, the observed signal is determined by the different latent variables. So if we use the different latent variable as input of the NSVE, and we can obtain the different of the signals. And the ZSAAD can be obtained by the different NSVE encoders. In the following experiment, we will disentangle the latent variables of the signal. Then we keep the speech latent variable and replace the noise latent variable, and we can obtain the different signal. First, let's see the original signal.
Yes. Each is still glorified as a national hero. Allow leeway. Rationalize all errors.
Greg Bias, fresh notice, weekday morning.
And next, let's see the modified signal. From the bubble 5 noise to the F15 10 dB noise.
Allow leeway. Rationalize all errors.
Greg Bias, fresh notice, weekday morning.
And this is the target signal.
Each is still glorified as a national hero.
We can find that
Allow leeway. Rationalize
our
all errors.
method, our algorithm changes the bubble noise to the F15 noise.
Yes.
So next, let's see the experimental result. In the second experiment, the methods are evaluated by the SISDR path and the story. And we use the Y to represent the reference method, and the PVAE represent our method. And this is the path and the SISDR comparison. And we can find that our proposed PVAE can always have the best performance than the reference method. And this is the story result. There is a similar conclusion. Here, note, we only use a basic neural network to verify our algorithm, and its performance can be further improved by using more advanced neural network. Finally, let's draw the conclusions. In this work, Bayesian permutation training DRL method is proposed to disentangle latent variables from the observed signal. And additionally, our method can not only successfully to disentangle different latent variables, but also obtain the higher SISDR and the PET score than the reference method. Finally, our speech enhancement, the reference method can achieve the better speech enhancement performance by introduce the representation learning. Thanks. That's all.